This is an introduction to hypothesis testing for a mean when sigma is known. That is, the standard deviation of the population is known. And so what we want to accomplish in this lesson is we want to be able to learn how to find p-values and interpret what they tell us. We want to be able to use p-values for a z-test for a mean, once again, when the population standard deviation sigma is known. We want to find critical values and rejection regions. And the rejection regions I'm going to put in a second video. So these last targets we're going to hit with a second video. So we talked in the previous video about the fact that we're going to use our p-value to help us make a decision about the null hypothesis. And so what we always do is we compare our p-value to the level of significance given. So if p is less than or equal to the level of significance given in the problem, we will reject the null. If p, on the other hand, is not less than or equal to and therefore greater than that level of significance, then we will fail to reject the null. So say we conduct a hypothesis test and we get a p-value equal to 0.0237. What decision would we make if our level of significance alpha was 0.05? Well, because p is less than or equal to 0.05, we would reject the HO. We have evidence to say that it isn't true. We have evidence in favor of our alternative, On the other hand, if a level of significance alpha were established at 0.01, clearly our p-value is greater than 0.01, and therefore we would fail to reject our null hypothesis. So we always compare our p-value to the level of significance provided in the problem. Now, to get this p-value, what we have to decide is, do we have a left-tailed test, do we have a right-tailed test, or do we have a two-tailed test? And here we're going to be using our table again to help us determine this p-value. So we know that our table gives us the area below a particular z-score. So we'll find a z-score. It's called a z-test statistic when you're doing a hypothesis test. And we'll look up that z-score in the table and we'll find our p-value there. If we're doing a right-tailed test, then we're going to have to take 1 minus the value we find in our table for the standard normal distribution. Because the table gives the area below, if we want the area above, we have to do 1 minus that number. If we're doing a two-tailed test, we're going to have to take 2 times the appropriate area in the table. And when I say appropriate area, that area may be the area below, depending upon where our test statistic lies, or the area above. We'll demonstrate this with an example. So we'll find our p-value using our table. So say we want to find a p-value for a left-tailed hypothesis test. We get a z-score of -2.23, and we're using an alpha level or level of significance equal to 0.01. So grab your table, and what we need to do is look up a z-score of -2.23. And of course we're using the table of standard normal probabilities, not the t-table. That's when we don't know sigma. Here we're giving you a z-test statistic. So if you go and find -2.23 in your table, what you see is a z of -2.23. 0.23, which would be right about here, has an area below it equal to, according to our table, 0.0129. We're doing a left-tailed test, so that's exactly what we want for our p-value. Our p-value would be 0.0129. So now we want to compare that 0.0129 to the alpha level given of 0.01. It's greater than that. So our decision here would be to fail to reject. It needs to be less than or equal to in order to be able to reject that null hypothesis. Here's an example where we get a test statistic of 2.14. So again, let's draw a picture. A test statistic of 0 would be right at the middle. 2.14 would be right about here. And when we go to our table, it gives us the area below. In this case, we are above the mean, or above the mean. And so we're basically looking for the area above. So when we look up our value, our 2.14 value in our table, it gives us this area below. And if you have your table in front of you, you should see that the area below given in that table for a z of 2.14 is 0.0162. Because we want the area above, we're going to need to take 1 minus that value. Oh, I'm sorry, I'm getting ahead of myself. 1 minus that value is 0.0162. The table gives us the area below, which is actually 0.9838. Sorry about that. So when we take 1 minus 0.9838 because we want the area above, that's when we get this area above equal to 0.0162. But because this is a two-tailed test, our p-value will be twice that area in the tail. So twice that area would be 2 times 0.0162. That gives us a p-value of 0.0324. If we're using a level of significance of 0.05, that is clearly below, less than or equal to 0.05, and therefore in this case we would reject the hoe, because in order to reject and say we have evidence against the null hypothesis, we need a p-value that is in fact less than or equal to the level of significance provided. Now just a note here, we're assuming that we know the standard deviation of the population. It will be given to us if we're doing a test about a mean and we're using z. But we also have to recognize that in order to be able to make a conclusion about the mean of a population from a hypothesis test, we have to have a random sample. Just like with confidence intervals, we need to know that either our population is normally distributed or that our sample size is large, and we know that for means, that means it has to be at least 30. If those two conditions are satisfied, then what we're going to do is compute our test statistic. We've seen this formula before. We're going to find out how different our sample mean is from our population mean. So we'll take x bar minus mu, and then we're going to divide by the standard error, which we know is our standard deviation of the population divided by the square root of n. That'll give us what's known as our z, but in a hypothesis test, that's called our standardized test statistic. So what we want to be able to do is, 1, verify that sigma, our population standard deviation, is known, that 2, the sample is random, and that 3, either the population is normally distributed or n is at least 30. Second, we want to state the claim mathematically and verbally. That may be in the null or the alternative depending upon the claim, and then identify what the null and alternative hypotheses are. 3, we want to specify a level of significance, alpha, and we will identify alpha based upon how strong the evidence how strong we need the evidence to be in order to be able to reject that null hypothesis. Fourth, we want to calculate that standardized test statistic that we just addressed, find out how different our sample mean is from our population mean, and then divide by the standard error. Fifth, find the area that corresponds to that z-score. It will either be the area below or the area above, and then use that area, 6th, to find the p-value. If we're doing a left-tailed test, that p-value, as we said, will be the number we find in our table for that z-score. If it's in a right-tailed test, it'll be 1 minus the number we find in our table, since our table gives us the less than. And if we're doing a two-tailed test, it'll be the area in the tail. That'll depend if it's left or right tail, and we'll have to double that value. Seventh, we'll need to make a decision whether or not we're going to reject the null hypothesis, and of course that depends upon how our p-value compares to our alpha. So if p is less than or equal to alpha, we'll reject the null. Otherwise, we will fail to reject the null. And 8th, we're going to interpret our decision about rejecting the null or not and put it in the context of the problem. So let's do this with an example. In auto racing, a pit crew claims that its mean pit stop time, so there's mu, is less than 13 seconds. Oh, that's a statement of inequality. We know the statement of inequality always belongs in the ha. So our ha will say that mu is less than 13. The ho, therefore, will be the complement of that, which is that mu is greater than or equal to 13. A random sample of 32 pit stops, so we can tell that n is 32, has a sample mean, that's x bar, of 12.9 seconds. Assume the standard deviation of the population, that's sigma, is 0.19. Is there enough evidence to support the claim at a level of significance alpha of 0.01? Sorry about that. Some of my formatting doesn't come through when I upload these to my application here. So first, we've identified our null and our alternative hypotheses, and we've identified also, as I was reading through the stem of the problem, the different values that they gave us and the variables that we use to represent those values. So now we want to make sure we understand that if we're doing a hypothesis test, we must have 1, a random sample, 2, either our population has to be normal or our sample size needs to be large. Well, we were told that our sample size is 32, that is greater than or equal to 30, and therefore our sample size is large. So third, we can go ahead and calculate our test statistic. And by the way, we know we're doing a z-test here, because again, we know we have been given the standard deviation of the population. And for means, that's what is required to be able to do a z-test. So we're doing a z-test, our conditions have been satisfied, our level of significance has been given to us at 0.01, so we're going to compare our p-value to that when we get to that point. All right, so fourth, let's calculate our standardized test statistic. So in a test for z, we take our sample average minus our population average and divide by our standard error. So in our case, our sample average was 12.9. Our population average that they claimed is right here in the null hypothesis, 13, and it always is in the null hypothesis. And we're going to divide by the standard error, which is our sigma, 0.19, divide by the square root of our sample size, 32. Now if you put this in your calculator, you want to remember, if you do this all in one step, this needs to be put in parentheses. So if you calculate this by hand, as I am here, you should find that we get a z equal to negative 2.98. So z is negative 2.98. Now keep in mind, we are running a left-tailed test. The table gives us the area in the left tail. Okay, so our fifth step is to find the area in that tail. So if I go to my table and I look up the area below negative 2.98, I do in fact find that the area there is 0.0014. That's my p-value. I do not need to double it. It is a left-tailed test. I only double it if I use a not equal to in my alternative. So that is my fifth step. Find the standardized test statistics. Sorry, that is my fifth step. Then find the area using our table. That area then, in our case here for a left-tailed test, is our p-value. Okay? So we now can move to step 7. Make a decision to reject or fail to reject the null. Well, 0.0014 is clearly less than our alpha level. 0.0014 is less than the alpha level of 0.01, and therefore we have evidence to reject the null hypothesis. It must be less than or equal to reject. If it is not less than or equal to, then we fail to reject. So finally, our last step in our hypothesis test, step 8, is to interpret the decision in the context of the original problem. And so at a 1% level of significance, we have sufficient evidence to reject the claim that greater than or equal to 13 seconds, or reject the null that greater than or equal to 13 seconds is required on average for the pit crew to change 4 new tires and fuel. Therefore, we can conclude that the mean pit stop time is less than 13. So we can conclude that the alternative is true. Okay? So when we reject the hoe, we have evidence to say that the alternative is true. So let me say that again. At the 1% level of significance, we have sufficient evidence to conclude that the mean pit stop time is less than 13 seconds.